Hi, everyone. Hello. Is this microphone working? It's just very quiet. All right, I will yell as loud as I can. Welcome to Colloquium, everyone. Thank you to one of the students in the front row who turned me from a classical entity into a quantum operator by putting a hat on me. Yes. No. Yeah. So today we have our very own Professor Ziqing Hong, my co-PI on a very exciting dark matter experiment that he'll be telling you about. He will also be talking about some fun experiments involving neutrinos. And for those of you who would like to visit him sometime, he has a lab in the basement with a beautiful ADR fridge that he's always happy to show off. Just beware that whenever you are around him, equipment tends to break, which is why the big projectors up top here gave us some trouble, and we're using this little one down here. So you just never know what's going to happen when you're around him. It's always an adventure. Without further ado, I will turn it over to Ziqing to talk about probing new physics with cryogenic detectors, literally the coolest physics around. And hopefully we will not put the cry in cryogenic today.
All right, thank you. Thanks. So am I audible for people in the back? Maybe, good. A little bit louder. Let me try this. Is this better? Okay, I'll do this. So yeah, thank you for coming here. And to just point out that there's this preset the date and time saying that some bug in the projector that we cannot fix. It requires a technology that is beyond what we have. So I suggest us schedule another colloquium with Boris soon enough to fix it. All right, so I'm talking about probing new physics with cryogenic detectors. So let's start asking ourselves, what is a new physics, or what is old physics, or physics that we understand now? Right, this is the physics we understand now. This is called the standard model of particle physics. And we've been spending, I don't know, 100 years on this. It describes the fundamental particles that makes up the universe. And we categorize those into a few categories. Like there are these quarks and leptons that we understand as they make up matter, right? Well, whatever matters we have around us, it's made of quarks and leptons. And then there's the force carriers on the right. These are the gauge bosons that carries the force, electro force, magnetic force, or weak force, or strong force, all of those forces that we are dealing with every day. And then there's this Higgs boson that's the central piece of standard model that I'll talk a little bit more about right here. So we understand that the standard model is, one of the model we use every day. It describes everything almost. It has been a great success till now. Well, one of the biggest success story is that the discovery of the Higgs boson. So the Higgs boson is like a particle that was predicted in the 1960s. People have thought, just from a pure theoretical point of view, people have thought about the existence of the particle long ago, like 50 years ago or 60 years ago. By the time of 1989, there's already a book published called the Higgs Hunter's Guide. So the series was saying, if you follow the book, if you work hard enough, you will find the Higgs boson. The experimentalists listen to it and keep working on it for like 30 more years. And then in 2012, at the Large Hadron Collider, both in ATLAS and CMS experiments, we simultaneously discovered this Higgs boson with a property that was predicted pretty precisely all the time. So you know, this is our the theory we are currently looking at. This is the standard model of particle physics. Then the question is, you know, if we already have such a successful story, such a successful model, what are we working on now in fundamental particle physics? The fundamental question is, does standard model describe everything perfectly well, right? Then the answer to that question is like, not quite. Right? We say standard model describes the electromagnetic force, the weak force, the strong force, but we know there's another source of force that is surrounding us every day. That's quite important to us. That's the gravity. And standard model does not describe gravity like at all. People have tried to put gravity into the standard model, and there's so far no like a successful attempt that can match both the theoretical point of view and the current data. So we still don't fully understand how our universe works. At least the standard model doesn't seem like a complete theory to the bare minimum. And then if you look at the whole budget of the universe, you might have seen this famous pie chart somewhere. The universe is estimated as like something like 70% of dark energy, 25% of dark matter, and all of the standard model matter, apologies, like the tag didn't show up very well. It's roughly 5%. So all the standard model, despite it is ultra successful, it only describes like 5% of the universe. So it leaves us to be wondering, how do we describe the rest of it, right? How do we describe what is the content of dark matter beyond we know it participates in gravitational forces, which the standard model doesn't describe either? Or how do we at all describe the dark energy? So everything in this table, despite how successful the model is, only describe this 5%. That's a little bit less satisfactory. And then if you look within the standard model, there are a few things that standard model kind of do fairly well, but not precisely. For example, when these are the last row, the green skies, these are the neutrinos. And these neutrinos in the standard model, we predicted them as they have zero mass, right, Ellie? But then the famous snow experiment have shown that these neutrinos would oscillate from one to another, which have to indicate that there are masses on the neutrino. The neutrinos have non-zero mass. And that goes against the prediction of the standard model, despite the mass is like super light, but they're non-zero. At least two of them are non-zero. And then there's a fundamental question of, we know these neutrinos, we know there are also antineutrinos, but we have not shown that whether neutrinos or antineutrinos are the same particle. We don't know. We assume they are different particles, but there's no data telling us one way or another. So there are all of these, just subtle or non-subtle things that makes us feel like the standard model, despite it's super successful, it's not quite satisfactory. That's why we are keeping working on the particle physics to sort of probe whether there are any new physics beyond the standard model that can unify our understanding of the whole universe, right? It's all driven by curiosity of us. And then, if you're a theorist, you can go to a blackboard and you derive your theory and scratch it and derive your theory and scratch it again. But I'm an experimentalist. So I asked myself, like, in my role, how do I work on this problem, right? And within the experiment community, there are people like the Atlas group who's doing this collider experiment, which are accelerating protons at up to enormous energy and let them collide with each other, so that you can look at the high energy spectrum of the standard model, hoping to produce new particles. That's one way to do it. And then there are another group of people who believe that neutrino is a key to understand physics beyond the standard model. So they're producing a intense neutrino beam somewhere in the national lab, send it through half of the crust of the Earth, and then build another big detector 1,000 kilometers away to see how the neutrino looks like right at its production versus after it traveled 1,000 kilometers. So that's another way to probe the physics beyond the standard model. The way I'm interested in, the way I'm currently working on is this rare event search. So why do we call our experiment rare event search? It's literally looking for a needle in a haystack, okay? So here are a few examples of how rare the rare event search experiments are, right? If you look at the typical dark matter experiment, you expect if you have a 30 kilogram of detector, you run it for a year, you expect one event, okay? So we need to either build bigger detectors, or we need to build a detector that's like ultra sensitive to even get to these events. And then if you are looking at the so-called neutrino-less double beta decay, which is probing whether the neutrino is its anti-particle or not, you build a detector of 500 kilograms, you expect one event per year. So again, fairly rare. And then if you are looking at this neutrino coherent scattering event that we'll talk about in just a bit, the situation is slightly better because we're using a fairly strong neutrino source. The situation is that if you have a 10 kilogram of detector, you can expect one event per year. The other thing to note is that when we're talking about Higgs boson, the mass of Higgs boson is something like 125 GeV. And when we're talking about these rare event search experiments, the energy we're talking about is very, very low. Like the WIMP energy is like less than 10 keV. And neutrino-less double beta decay is fairly energetic in our field, which is like in the MeV range. Well, the seventh is like way below 1 keV energy that we are seeing. So we are calling for a large enough detector with ultra sensitivity, like below keV sensitivity or way below keV sensitivity. So how to build an experiment to look for such a rare signal that's hidden within the haystack is the challenge of this field. All right, so let's start with the dark matter search as an example. And the reason why we believe that dark matter is out there, there are abundant of evidences, right? One of them is the following. So this is a classic galactic rotation curve. So the way to think about it is the following. So if I have for example, the Earth rotating around the sun, I can calculate from Newtonian gravity. I can calculate the function of the rotation speed or rotation velocity as a function of the distance from the Earth to the sun, right? That's fairly easily calculable. If I extend the calculation to a galaxy or galaxy cluster, the same physics applies, right? We will still get the mass to cancel out the mass of the galaxy or the star itself. It's going to go around the center of the galaxy or center of the galaxy cluster. But in order to do that calculation, we do need to know the mass or mass distribution of this galaxy. Then we make an assumption. The assumption is like, if I look at a specific spot in the sky, the brighter I see, the more mass there are. Okay, that's a very simple, like one constant assumption. The brighter I see in a specific area in the universe, the more mass there are. Then if I make that assumption, I can then derive, I can then observe a mass profile as a function of the distance from the center, right? Then with the mass profile, I can derive an expected function of the velocity as a function of the distance. It's basically the lower curve. You expect the velocity to go up within the visible area of the galaxy, because you are getting pulled more and more by things that's in the within your orbit area. But then once you go out of the visible disk, you expect the velocity to drop, because you have only so much pull with your gravity. As you go further, your velocity is expected to drop. But what is observed is the following. The velocity is roughly a constant as a function of like distance to the center. Okay. That means, one of the two things could happen. Could be that our calculation is wrong. Now you say, Newtonian gravity is not that precise. Let me repeat it with general relativity, and you get the same result. Or maybe your general relativity is like, we need to modify that. Okay. Possible. There are people working on that. Or it could be that our first assumption that the amount of mass is proportional to the amount of light we've seen in the galaxy. That assumption is incorrect. Okay. It could totally be that there are mass that we're not seeing. And those mass is providing the extra gravitational pull to whatever is rotating around the galaxy. Okay, so that is what we call darkness. That's why we call this thing, we call this substance dark matter. It is matter because it does provide gravitational pulls, but it is dark because it's not emitting light. And then if you do some calculation and with other data, you measure the budget of the energy of the universe, you realize in order to achieve a rotation curve like that, you actually need to add in quite more dark matter than the normal matter to make the data fit. Right. So the current best fit is that the amount of dark matter is a factor of 5 as the amount of regular matter. So that leaves a lot of curiosity, right? We need to study it. And now, of course, there's the thing that's called dark energy, and I know very little about it. So don't ask me questions about dark energy. Okay. Here's another sort of compelling evidence that you might see here. Or floating around on the internet. The idea is the following. So this is by observing the same spot in the sky with two different technologies. You look at it with photons or with light, or you look at it with the so-called gravitational lensing. That is measuring how much gravitational pull there is to bend the light going around it. Okay, you do the same measurement, or you do the two different measurements at to the same spot in the sky, and at this particular site, you realize the two results don't agree with each other. And then you think about, hey, what's going on? A best story that we could come up so far is that this could have been just a car crash scene of two galaxies. So if you think about two galaxies just minding their own business and all of a sudden they run into each other, whatever, thank you. That means I need to wrap up this story. Okay, whatever mass that is participating in the electromagnetic interaction, or whatever interaction that we can we know and love, they will see each other. So if you say, I have two galaxies run into each other, they'll slow down. But there is this and that blue lump, they just go past each other as if they are never interacting with each other, right? So this will feed the hypothesis that in each galaxy, there might be a population of the standard model particle which would interact with each other, and another population of dark matter, which would very weakly interact with each other. Then when the two galaxies collide with each other, the standard model parts that emit light got slowed down. And the dark matter just moves on as if nothing happened. So that's another piece of evidence of this dark matter theory that make us believe that we should look into this like 5 times more mass than what we know, right? Hope that I've convinced you that dark matter is something that we should look into, and there are multiple ways to look into it. So you either try to produce it in the collider. This is a pseudo Feynman diagram that we usually use. You can have standard model and standard model particle coming in, and with whatever interactions in the middle, you can produce a pair of dark matter particles. Then you look for signatures of these dark matter particles in the collider. Or you flip the Feynman diagrams around. You say, at the beginning of the universe, there might be a lot of dark matter floating around, and they go through the same interaction, and they annihilate into standard model particles. And a lot of those standard model particles, we hope, are just photons or electron positrons, so that if we just look into the universe and we see, for example, there's a lot of 3 keV photons running around for no reason that could be from this self-annihilation process that happened early on in the universe. That's what we call the indirect search. And the thing we're doing here is that we're doing this direct search, which is we're making a detector as big as we can afford, or as big as the funding agencies allows us to build. We make it as good as possible, and we wait for the dark matter to come in and scatter. Okay? The standard model part is just my detector. And the dark matter part comes in and scatter, and my standard model particle would pick up a little bit of energy or momentum. So we need to build a really, really good detector to see that little kick from inside of my detector. All right. So if you've accepted that there are dark matter, and their detection is one way to try to approach it, then we can get down to a little bit of mass and try to estimate whether this experiment is feasible. Right? Then we look around us, and we're somewhere here in the Milky Way, and we on the Earth is rotating around the sun, and the sun is rotating around something. Well, we're all moving. Turns out that we're moving at a relative speed of something like 230 kilometers per second. Even if you just sit here still, you're still moving at 230 kilometers per second. Then if you, from the rotation curve or other ways, you can estimate what is the dark matter density around here. It's quite a bit, right? Then you assume, like, say, my dark matter is something like 1 GeV per mass, and you do the calculation. I extend my hand out. How many dark matters particles are going through my hand per second? And you end up with a quite big number. It's like something like 20 million of dark matter particles is going through my hand every second. Okay. So we're not lack of dark matter sources. Then the naive idea of, like, how do we do this measurement? Simple, right? You get a detector. You put it on the Earth. You wait for dark matter to come in, scatter, and you find the signal in your detector, right? Now the question is like, if it's that simple, why haven't we seen it? Right? Seems like an easy experiment to do. There are two possibilities. One is that maybe there's a huge flux of dark matter coming through all the time, but they rarely interact. So in the technical jargon, it's like the interaction cross-section is low. So how do we deal with that? Just build a bigger and bigger and bigger detector, and just make the interaction number high. That's one possibility. The second possibility is that, okay, dark matter do come in all the time, and they do interact all the time. But every time they interact, it leaves a tiny bit of energy, so that the previous generation of detector was not precise enough to see them, right? So in that scenario, our goal is also clear. We just build a better detector. This is the experiment we came up with. This is called supercilium as Snow Lab. So Snow Lab is somewhere like, if you drive from here north for 4 hours, you end up in the town called Sudbury, and they have a lot of mining activities in Sudbury. And in one of the mines that's 2 kilometers underground, they build a lab. Okay, so every day if you want to go to Snow Lab, you drive to the site, you take a cage down 2 kilometers. It doesn't take a long time, 3 minutes. So you're traveling actually vertically at a really high speed, as if you're driving on the highway. Then you walk horizontally by like 2 kilometers. You find yourself inside of this like huge, clean lab that's perfect for doing science, right? Then within this lab, we're planning on building this big monster. I guess we did not do the Euro thing of putting a person in the diagram, but basically, let's see, this green thing is something like 5 meters across. It's an experiment of the size of the room with all of these complicated things that is supporting the experiment. I'll make a brief note that we do have a friendly neighbor that we call Qt, and we'll talk a little bit about that later. So we said we're looking for dark matter, but do we have a model, a specific model that we are looking for, right? Different dark matter will show up differently in your detector. It turns out that in something like, this is 2017, people did a survey of the whole field and say, hey, how many dark matter models do we believe in? And it turns out like there are a lot. The mass of individual dark matter particle, or well, at some point it's no longer a particle, ranges from like ZeV, which is 10 to the minus, I don't know how many, a lot, to like 30 times the solar mass. So this basically tells us like, we don't really know what we're doing. But that's until we find the dark matter, we are sort of just exploring, right? That's normal. So what do? You based on the sensitivity of your own experiment, and you draw a circle, and you say, you know, the experiment I'm building, or we're building as a team, I'll show how big the team even at U of T is focusing on this circle, like nuclear recoil dark matter around a GeV. This circle, electron recoil dark matter around MEV. And this circle, the absorption dark matter around the EV scale, between EV and KEV. So, you know, we don't know precisely where the dark matter mass or model lands, but we're going to do our best and look really hard in wherever our detector is the most sensitive. Then if we just think about one specific most better motivated model, the so-called WIMP model, weakly interacting massive particle model. this is a plot that you often see in dark matter direct detection field. So the way to think about this plot is that the x-axis is what is the mass of each dark matter particle. And y-axis is the interaction cross-section. Each of these solid line is that one experiment came in, did their measurement for multi-years, and they have not seen dark matter. Thus, they draw a line and say, whatever dark matter is, it cannot be, for example, a mass of 100 GeV if I look at this line, and with a cross-section that is higher than 10 to the 44th. Okay, that's an exclusion curve. So people have been doing this business for 20 years, and we haven't seen the dark matter particle. So there are all of these exclusion curves that people try to draw, and all of these dashed lines are the projected sensitivity. Like if I build the next generation experiment, how much of a parameter space I expect to probe. And the idea is that if you want to go down, you build a bigger detector. If you want to go to the left, meaning if you want to probe dark matter with a lighter mass, you need to build a more sensitive detector. And we are sort of looking in this corner, right? And this is the design of the whole super CDMS Snow Lab experiment. The idea is that we have these detectors, sensitive detector that we'll talk a little bit about in the next few slides. And think about this searching for a needle in the haystack problem. The reason why the experiment is hard is not only because the needle is thin, it's also because the haystack is huge. So we need to try to shield against a lot of our background. And this is why the experiment is surrounded by layers and layers and layers of shielding. And we did a careful estimation of with this shielding material, how much residual background we will have within our detector. And then as we'll talk in just a bit, our detector actually works at 15 millikelvin temperature. It's like 0.015 Kelvin above absolute zero. So that needs quite a bit of cooling. Like there's a dilution refrigerator here that runs like 2 pulse tubes or something, and there are like 5 more pulse tubes running on the other side. So it takes a lot of effort to cool this experiment down. And our initial payload is going to be 4 stacks of 6 detectors, and I'll show you one stack in a bit. And we have also a lot of vibration isolation requirement. Among all, this experiment is actually in an active mine. Snow Lab is 2 kilometers underground, and we have this access because the mining company is still doing mining there. Every once in a while, they're going to set something off and blow off a bunch of rock, and they're going to scoop out to make profit. So our experiment cannot be monitoring the mining activity. So this whole thing is built on top of the seismic platform that is isolating all of us from the rest of the mine. Okay. Then, and talking about direct detection, our strategy is simple, right? You get a bunch of particles, standard model particles, or detector, and you wait for dark matter to go in and scatter. When that happens, you get 1 of 3 things, maybe 2 of 3 things. You either get ionization, and you'll see charge in your crystal, or you'll get scintillation, and you'll see light in your crystal. But among all, second law of thermodynamics tells us everything turns into heat at the end of the day. So when a recoil happens, or a dark matter coming back into your detector, what is guaranteed is that it will generate heat. So if you can measure the heat signal, you'll get the ultimate sensitivity of the signal. Okay, so then here is the sort of Venn diagram of the signal we're looking at, and in heat or phonons, we're guaranteed to get 100% of the energy that the particle deposited. So this will be the more sensitive channel that we're looking at. The way we look at heat is from the surface level, simple. You get an absorber, right? Your whatever detector material, and you cool it down to like almost zero degree. This is by, you get a crystal and you bolt it into the dilution refrigerator. You cool down your refrigerator. If you're lucky, it goes to 50 millikelvin, and your crystal ends up at 50 millikelvin. At that point, you greatly suppress the thermal phonon population. Right, inside of your detector is like very quiet. Then you put a thermometer on your detector, and you just measure like whenever the crystal heats up. Right, easy enough. How do you design your thermometer? It's also quite simple. We use superconductor technology. We find a chunk of superconductor, a chunk of metal, and we tune its critical temperature to be quite low, like say 100 millikelvin, right? And we cool it down not below its superconducting transition. We cool it down to right in the middle of its superconducting transition, okay? We figure out a way to keep this chunk of metal in the middle of its transition. We don't want it to go normal. We don't want it to go superconducting. We keep it in the middle. So whenever there's a puff of heat that comes in to the sensor, it will drive the sensor up in temperature. But since it's riding on this transition curve, the transition curve is fairly steep. A tiny heat would turn into a significant amount of change in the resistance. And if we just measure the resistance of the superconductor, you get a pulse. The larger the energy, the larger the pulse. Okay. In reality, this is a photo of one of our detectors. The size of this is like 1 centimeter by 1 centimeter by 4 millimeter. You can pick it up with your hand. And each individual little cell on top of the crystal is one of these, what we call TS cell, right? The thermometer is basically just deposited directly onto the crystal for best thermalization, okay? So this is how we just use a chunk of superconductor to turn it into the most sensitive thermometer, and we use that to measure the temperature of the crystal. Okay. Then if we want to, we say we want to build big detectors, right? There are, whenever you build these detectors, there are different optimization schemes you can use. We have kind of two different optimization schemes. So in SuperCDMS Snow Lab, each detector, and I keep promising things. I have a photo later on. Each of these is sort of 1 kilogram. And if you optimize the detector so that you measure both phonon and ionization, you measure heat and charge, you can sort of tell where the signal is coming from. At least you can tell whether it's a photon that just hit my detector or it's a dark matter that just hit my detector. Or you can invoke this like internal amplification scheme, which we call the look effect. You can internally amplify the signal so that you achieve the ultimate sensitivity towards the lowest energy deposition. So we're playing around a lot with this detector optimization scheme to achieve the best sensitivity. All right, okay, here's the photo of one of these detectors. This is the IZIP detector that I just talked about. It does the charge and phonon dual readout that give you the so-called electron record, nuclear record discrimination. And then this is a HV detector, which is again roughly 1 kilogram big, and you just internally boost the signal to extreme to achieve the best sensitivity we can have. Right. Then, once we have the bigger the detector that we build, we do need to understand the haystack a little bit, because after all, it is beneficial if we can reduce the size of the haystack. So in order to do that, we have a really strict program, like every single pin, every single material that goes into the experiment has been pre-screened, and the radioactivity of the material has been recorded. Not even that, we record down to hours how long each piece of the material stayed at sea level. Because every time you put a piece of material at sea level without shielding, it gets activated by cosmic rays. So we record down to the precision of hours, how long has our crystal, like silicon or germanium, sit at sea level? How long has our copper sit at sea level? And we try to minimize that amount of time by, whenever we've done something with the detector, we immediately ship it underground for storage. And then if we need to do the next step of processing, we put it out, do something on it, and immediately ship it underground as well. So we keep close track of our haystack. All right. So this is the photo of a so-called detector tower, 6 detectors stacked at the bottom, and readout electronics on the top. And the idea is to just put this into that, right? And if you go underground now or today, well, I was there Monday. We have finished that. We have finished that. We have finished that. Some progress, not quite impressive. But if you look at this, this is the overview of the lab that's taken in July 2012. And this is what it looks like now, as of yesterday. We have done a lot of progress. And you can imagine if you extrapolate this progress, we're going to start data taking next year, we hope. All right. So coming back to this friendly neighbor that we just talked about. So this is actually another cryogenic facility that a subset of the collaborator have built that's sitting next to Super CMS. This is a dilution refrigerator as well. It goes down to 15 millikelvin. And the purpose of building this facility is like, we want to test our detector before we finish this big project. It'll kind of be bad if, we have finished this like room size experiment and put our detectors in, and the detector that didn't quite work. So as of last year, we actually put one detector into this facility. And we have proved to ourselves that, yes, this detector does work. And we know how to operate this detector in the underground environment. Because every time you need to go down, you take the 3-minute cage down, you do a hike, you clean yourself, you go in and mess with it. With like a few months of effort, we were able to fairly well calibrate our detector to a very good precision. Okay. We have live data saying our detector is working, right? And while we are building up this big experiment, we're also trying to say, hey, can we push this technology a little bit further? And that is by doing all of these prototype detectors. And we call this detector HVEV. That's a grand scale detector. And we achieve like EV level resolution, right? That's like the state of the art. Nobody has achieved it before. And we run these detectors. Well, we don't need to run it deep underground. Well, we can. But there are more facilities that we run it, especially this guy. If you have been to the basement and looked in my lab, this guy is actually parking in my lab right now. And we have access to another facility that's 100 meters underground at Fermilab. This is called Nexus, right? So the performance of this detector is just fabulous. The previous generation, I'm already seeing the previous generation, and this was the state of the art, is that it has 3 EV resolution. which means if you shoot photons at it and you internal boost it a little bit at 100 volts, you can measure 1, 2, 3, 4, 5, all the way to many photons, individual photons in your detector. Okay, and we can calibrate this detector all the way up to like 5 decades of dynamic range. We can calibrate it to hundreds of keV. So it's a wide range, but super precise detector. And we use this detector to do not only the photon calibration, but the neutron calibration. As we said, if a neutron comes in, it'll interact with the detector a little bit differently from the photons. But if you have like individual excitations, you expect to see quantized behavior. And we did. This is where we put the detector into a neutron beam and do the classical neutron scattering experiment. We see like a very, very good performance. All right. And I was saying like that was the last generation detector. We recently tuned up a detector where the publicly available resolution is like 1.1 eV. And this is already below the silicon bandgap. So we have a detector that can probe physics below the silicon bandgap. And we actually improved it upon this already as of a few months ago. So, okay, that's everything we've been doing with dark matter. So for the next few minutes, I'm going to say, we're actually going beyond the current generation of dark matter detection and think, hey, we've been seeing these blue things. What are they? They're actually solar neutrinos come into your detector, mimicking the signal as a dark matter. So we better understand it before we already hit that intrinsic background of our dark matter detection. And this interaction is through the so-called coherent elastic neutrino nuclear scattering process. The idea is the following. If you have a neutrino coming in, and the neutrino have low enough energy, the Broglie wavelength of the neutrino is going to be big. And if you have low enough energy, so that the Broglie wavelength of the neutrino is like of the size of the whole nucleus, the neutrino is not going to interact just with a quark or a proton, but it's going to interact with the whole nucleus. And if you have a big nucleus, you enhance your cross-section by many orders of magnitude. That is why you very quickly hit this neutrino fog, as we call it, only in the low energy part, because the cross-section is so big. And the way we are sort of getting ahead of the curve is that we're going to find a source of these neutrinos and study it carefully. The experiment is called Ricochet. It's a neutrino, a reactor neutrino observatory. Okay, where can you find the most amount of the most intense neutrino source on Earth? You go to a nuclear reactor, and you park your detector, a dilution refrigerator next to it, and you start measuring. Okay, this is actually happening in. Yes, this is where it's happening. It's in Grenoble, France, in the mountain village in the Alps. And that's a very friendly dome which hosts a research reactor. And let me see, our experiment is basically here. That's 7 meters away from the core of the reactor. We get as close as we can. And then we fill the space as we can with shielding material, because you still need to decrease your heat stack. And we measured, this is the green is the neutrino signal we expect, and the blue is the measured background. So we expect that with a bit of operation, a few years of operation, as long as we have a detector that can go down to this energy, we will be able to see a bunch of neutrinos on top of the background. Okay, the status of this the experiment that we have this beautiful, we call it planar and FID detector, and we put it into an array. This array exists, and the three detector array already exists. And the ultimate goal of next spring is to build this 18 detector array. And as of last year, or well, this year, we have put the detector in, put the fridge in, put the detector in, and we have got data. And this is the reactor off data, and this is the reactor on data. And you can see that, yes, with the reactor turned down, there are a lot of things going on, and the detector performance decreased a little bit, but not by that much. It's achieved ionization resolution of like 40 something EV and heat resolution of like less than 30 EV. World leading detector, for sure. The idea is that we're going to put in the full detector array next spring, run it for like 2 years. And then we're fairly certain that we will be the first experiment that observe this 7th process in a reactor. And then we're not satisfied by that. Remember we were talking about this 1 EV resolution prototype. We're thinking about using this technology as well, and putting this newly developed detector into the detector array, or something similar to this. There's a little bit of complication, because that was 1 gram, and we need something like 1 kilogram. So we need a way to read out 1,000 detectors in a row. That is what we call here, the microwave multiplexing. So since I'm running out of time, I'm not gonna get into here, but just to say briefly mention the conclusion that, we're probing physics beyond the stand model. We're doing dark matter, we're doing neutrino, we're doing everything we can, and we're doing it all with these super precision cryogenic detectors. And the last slide is about our team. We have a big team here. That's only half of that. The rest. Thank you.